Okay, well, welcome back to E443, 543. We're going to continue where we were last week. I appreciate your patience about getting things set up, and maybe Giuliano and company can help us if people are stuck. At the moment, I can't get into NanoHub, so we'll see what happens. In terms of that, I have Twitted open on my desktop if we need it. And today we're going to continue our discussion about how you control cell attributes and start thinking about what reasonable models look like. And I need to remind you, as usual, that this is being live streamed and recorded. So please keep that in mind when we go forward. Today, I'd like to quickly go through everybody's project ideas, and then I want to talk a little bit about the homework. Then we're going to dive into a series of exercises that address how you set cell attributes. And we're going to talk a little bit about starting in Python to do computations. I hope we'll do some scientific plots, which are one of the things that CompuCell is pretty good at, I hope. And we'll take things from there. So I want to come back. I want to first make a comment on the homeworks, not that you handed in today, since I haven't seen those yet, but from the previous week. I think people thought quite a bit about modeling and some of the issues that were raised in that handout that I gave you about the process of modeling. And people thought a lot about project ideas. And there were some very interesting and exciting project ideas. I think one thing I'd encourage you to do is, again, it's not a requirement, but I do encourage people to think about working in teams. There are people with all sorts of different backgrounds and expertise, and working in a pair might not be a bad way of dealing with that. And I also encourage people to try to be flexible and not too ambitious. Especially, I would encourage you to find papers that have done simulations of the problems you're interested in and ask the question, are they something that reasonably could be done in the course of a semester? I realize sometimes that if you have a very specific interest, it's disappointing not to work on that specific problem. But it's also important to be able to get something started. And so if your ideal project is very ambitious, I would encourage you to try to think about perhaps scaling it back a little bit and ask the question, is there something achievable that you could do during a semester that would be a first step towards that project? And I would like people who are enrolled in the class to try to meet with me, if it's not for an hour, just for half an hour, between now and the end of the weekend, between now and Sunday night, to try to talk about projects one-on-one so that we could come up with some practical projects, ideas. Again, some people had everyone had interesting project ideas. And they were all good ideas, but my main concern is just to make sure that people don't get stuck with a situation where you pick something really hard and then at the end of the semester you haven't done it. And so I encourage people to be focused on the achievable, even if it's not the ideal. So does anybody have anything that they want to talk about today briefly about their project ideas as an update? Let's go around the room. Joel, do you have anything you want to talk about? And our auditors are fine. If your auditors have suggestions for projects that they think somebody else should be doing, that's fine too. You're welcome to participate in any way you choose. Joel, start with you.
Yeah, I'm still, I think I mentioned this on the last class that we had last week. I am doing the necrotizing enterocolitis. Uh, but you and me had a personal talk. I don't know if I'm going to keep going with this project or not. I think it's an easy one because the calculations for the functions are all already done. We just need to, um, move this to the CC3D. So even if I don't do this paper or this model, maybe someone else that doesn't have an idea or not confident with the idea or is too hard, it's probably a good thing to pass on. So there's that too. I can show you the screen and the paper. The paper I have to look it up, but yeah, it's not too hard. All the calculations and the way things are supposed to be are already accounted for. We just need to implement in CC3D.
So that may be a good, as I say, we should probably sit down and look at the paper together. And again, presenting it might not be a bad idea. As I say, I'd like to encourage people to think about pairing up. And so there was one person asked a question about the project, which was, if you change your mind, can you change your idea? And the answer, of course, is yes. The only thing that I want people to do is to try to make those, to try to come up with a go no go on a project idea early, so that you have enough time to think of another project if your first one doesn't work out. And so the key thing here is to make sure that if you try something and it's not going to work, you have enough time during the semester to recover from that.
Right. If
It's
people
not
want,
the
I can,
no, go
sorry.
ahead.
If people want, I can share the paper and they can take a look and see what they think.
I mean, that's also not a bad idea. If people would like to distribute the papers you're thinking about through the email list, or maybe send them to Giuliano, and Giuliano could put them up in the files directory in the Canvas. That wouldn't be bad either. And I encourage people to meet offline, online, but off out of class time, to talk about these possibilities. Next week, you'll have time to present these ideas a little bit more, but I just want to make sure that people are thinking about it. Joel, did you have anything you wanted to screen share, or is that, or that do you want us to come back to you later?
Yeah, I can screen share. Let me
Okay.
just do it. Yeah, so this is just a supplemental table that is the most important part for us, I guess. Uh, and they already accounted for, as I was mentioning. Yeah, he's using a hill function here to account for nutrition, the consumption of the nutrients, and so on. So it seems that is very well done, very well documented, which is most important for us. This is not actually the paper. The paper is here, and we can probably follow just the same model and implement. So it doesn't seem too hard.
Okay, I mean, I think there are two kinds of hard, one of which is a structurally hard problem, and the other one of which is whether you can get how to get meaningful results out of the problem. And so we should probably talk when people present their uh, project ideas. I think it's important to do a slide or two of context. What's
Mhm.
the situation? What's the project about? What does the model calculate? So it's why is this an interesting problem? And then absolutely dive into the mechanics of what it is that makes it a reasonable thing to do. But in terms of addressing things for the audience, for the class as a whole, I think it's important to give some background ideas as well.
Okay. If you want, I can talk a little bit about this very quickly. I think I
Okay.
mentioned in past on the first week, but this paper is basically trying to explain how necrosis is initiated on this specific disease. They had a hypothesis there was some product that was not getting cleaned by the cells at a reasonable time, and that was initiating the necrosis. But as their models show, there's more things involved than just the cleaning of OS. So they don't dive too much in the second hypothesis that they noticed that that there is a correlation between the mucus and the TRL4 activation that causes the necrosis, but it didn't seem that they went too deep in that. And maybe that's the opportunity for us to try to explore more of that and see how it actually works and what is the mechanic involved.
Okay, great. And people don't have to be today saying so much, although it's fine if you do. I just want to make sure that everyone is thinking about these problems and moving forward. Connor, do you have any?
Yeah, so since we last had this group discussion, I was reflecting on the two ideas that I mentioned, and I think it's a pretty safe bet that the ideas that I was having about viability spaces is not something that can be feasibly done in a semester. So I'm officially pivoting in kind of the minimally cognitive cellular to multicellular direction. And right now I'm still going through the papers that you emailed me, Professor Glazier, but I think that that is probably going to be the direction that I head in, trying to replicate and mess around with some of that stuff. Just haven't fully zeroed in yet.
That's fine. Alex.
I have not had time to think of the project more. I have a paper deadline on Thursday.
Okay. I know we have some auditors, but you're welcome to kick in. Jessica, any suggestions for us?
No, not off the top of my head.
Andrew?
Is my volume okay? All right, so I've been interested in the slime mold papers, and two that have popped up for me are the how amoeboids self-organize into a fruiting body, and then there's also morphogenesis. So those are the two papers I've been thinking about.
Those are good papers, and they were to some extent the inspiration for CompuCell. And so it's moderately embarrassing that we've never replicated them in CompuCell. The one thing that we tend to run into with some of those papers is that the time stepping that they use is very, very short. And so the simulations take a very long time to run. And I don't think that that's intrinsic to the problem. I think it's possible to work around that. But last year, we had a student who worked on one of those papers, and she was able to replicate a good chunk of it, but it was frustrating because the simulations took a lot of time steps. And so we should sit down together and go over the particular papers you're interested in and think about how we can possibly make sure that that you can do that work in a way that is achievable. There may be some related papers by other people. I think Bakhtiar Vasiev, for example, did some papers on slime mold movement, where some of the methodologies may be a little bit easier to replicate. And so I think doing the slime mold simulations would be great, and I'd love to see that happen. Both that basic early aggregation where the cells are moving independently of each other, and then the aggregate crawling. And I just want to make sure that we do it in a way that makes that is not frustrating, because I think that is achievable. I've written some simulations of that kind, and it does work. But sometimes directly translating the source papers, if they didn't think about how long it took to run the individual simulations, which sometimes they don't, you want to be careful, a little bit careful about that. So let's talk about that together. But I think that's a good project.
Definitely some things to consider. Thanks for the feedback.
Jackson.
I don't know if I really have anything new. I'm just still trying to like, I have like a lot of different ideas. I'm still trying to kind of research. Because one of the things you said was that like blood's hard to model. And one of the project ideas I had was like a snake enzymes and its effect on blood platelets. So I was kind of looking at instead its effect on muscle cells and muscle degeneration. Modeling that maybe.
So we're working with a group at the moment in Virginia, University of Virginia, that's interested in muscle degenerative muscular diseases. But that work of theirs hasn't been published. At least their CompuCell related work hasn't been published. People have done coagulation in blood models not using CompuCell directly, but using methods that are comparable to CompuCell. The thing you want to probably be careful about is blood flow, because if you're actually doing fluid dynamics, that's computationally very expensive. And so things like adhesion of leukocytes to the wall of blood vessels and their binding, those are very, very elaborate simulations. People like Roger Kam and Karniadakis have spent many, many years developing simulations of that kind. And it requires essentially supercomputing capability and a lot of code. And so I think those kinds of questions are fascinating, but they may not be, and longer term, those are great things to work on. But during a semester, I would say that those are hard problems. But there is a paper by Mark Alber and, oh shoot, he's at the med school. He's at IU School of Medicine on coagulation, blood coagulation. Not thinking about flow so much, but just the cascade of factors that are triggered during injury, and that paper might be reproducible. So I'm not saying that clotting by itself is a bad idea. I would just steer away from anything that involves explicit simulation of the flow of blood. And so we might be able to do a little bit of Googling together and see if we can find a paper on clotting that met some of your interests and at the same time was more achievable.
Sure.
Josh?
Hey, so I have over the past week, I also have been interested in looking into slime mold simulations. So may I share my screen?
Please, go ahead.
So I found two papers. This one, I actually heard about this a while ago. They placed food sources in a pattern corresponding to miniature relative positions to cities around Tokyo, and then grew a slime mold, and they found that it actually like replicated the Tokyo railway system. And I thought that was pretty interesting. But then I found this paper. It was in the preliminary project assignment. I believe it's a bachelor's thesis. And he essentially created a CompuCell simulation where you can like place food sources and stuff like that, and then look at the networks. There's some figures at the bottom. Yeah. So my idea was I control F and I don't see NanoHub anywhere on here. So there's, to my knowledge, no existing NanoHub application of this. And then as you can see, the food source locations that he does, some of them they're not really as complicated as the ones in this one. So I was thinking it'd be maybe good to turn that into an app and then maybe do more complex food systems.
I think that's great. I mean, it's a nice proof of concept when somebody's done it. And it's extra nice when they've done something that's basic but has lots of room for expansion. So I think that's a great one. So if Andrew is interested in that as well, then that's something maybe you could talk together and see whether that's a project that would be doable as a team.
Yeah, and also I was wondering, when you were speaking with Andrew, you were talking about computational cost. I remember, can you run any CompuCell simulations on like clusters or anything? Because maybe that could be a potential option. Or
yeah. So I mean, if you need, TJ and Giuliano can show you how to run on Big Red, and we run on clusters all the time. The thing about running on clusters is if you need to run tens of thousands of simulations or thousands of simulations, it's great, but it's not fast. And so there's a bit of a tension a little bit between writing research project code and writing NanoHub code. Because the whole idea of a NanoHub is essentially educational demos where you run it in real time and you see what's happening and you interact with it. And that limits to some extent the level of detail and the complexity of the simulations you can run. For research purposes, if the simulation takes a day to run, that's not a problem. You run 100 of them at once. You come back a day later and you have 100 simulations. And so I think that running on clusters is absolutely a reasonable thing to do. But it's not essential that there be a fast version of the code to run locally or to run on NanoHub as a demo. But I mean, one of the reasons we picked that NanoHub example was to encourage people to try to do simulations that ran fast enough that during the lifetime of the class, 14, 16 weeks, you'd have enough times to rerun it that you could develop code. And so, but absolutely, if you're interested in pursuing it further and want to run it on a high performance machine, you can do that. In principle, NanoHub provides access to some high performance clusters.
Yeah, because I remember when I was taking Vikram's class, we did a simulation of ions and nano confinement or something like that. And there's an option where you could either run it locally or on a cluster. So I was thinking maybe something like that, or depending on the complexity.
We can look into that. But we tend to run, when we run on clusters, we tend to run in batch mode. And so we haven't explored the idea of having an interactive front end and then having a back end of cluster execution.
Okay.
But that's certainly a possibility. And if somebody wanted to look into that for us with NanoHub, we'd be very grateful. It would be well worth doing it, but it's not something that we've done so far. And again, part of that is simply because people haven't suggested it. And so.
Okay.
Does anybody else want to speak up and talk about ideas today? Again, our auditors are welcome to suggest project ideas. You can drum up business if you have a project you're working on in the lab you'd like to see a simulation created of. This is an opportunity. And auditors, if you want to present concepts, show us a few slides about the project you're working on as part of the project definition cycle, we'd be happy to take the time to do that. That's fine.
Hi,
so I don't know what. Please go ahead.
Present something? Yeah.
Please go ahead.
Hi. Okay, so I so you know that I'm working on the plant cells, and we want to model the calcium signal spread in plant cells. So because our project is still at a very we just started the project, and we haven't gathered enough data yet. But I think there might be a good practice for us try to recapitulate some of the published models. And there is a paper about modeling the calcium wave propagation speed in plant root cells. But it is a one-dimensional model. So what they want to test is just the speed of the wave. But they do consider like the cell. They think the distance between cells, and also the number of the calcium channels on the membranes. If those factors affect the wave speed, and they have the equation for the calcium diffusion speed. But for plant cells, you know, it's not like animal cells. It has a very big central vacuole, and those calcium channels are located on the vacuole. So the signal propagation only happens in the cortical cytoplasm. So when you want to model those cells, simulate those cells, it must be a different design. So I think I can send you the paper, and we can see whether this is something that we can practice to model for.
So one thing, I mean, CompuCell's diffusion solvers have some limitations, but one thing that you can do in the diffusion solver is define the domain over which diffusion happens. So you can define a cell. I mean, suppose you had just some square rectangular cell.
Yep.
You say there's a big hole in the middle where there's no diffusion, and there's only diffusion on the boundary.
Yeah, on the edge. Yeah.
Right. That you can do in CompuCell.
Okay, yeah, that's great. I assume the software can do that, because I see you can design those bulk cells around just at the edge. Yeah, yeah, that's great.
So the thing that's missing in CompuCell are the idea of active pumps. So ion channels that are passive channels, Fickian channels, where the diffusion is proportional concentration. That's something that's doable easily. But if you actually have an active transporter, like a ion pump or an antiport or something like this, those would have to be done probably by hand. And it's not that you can't do it. You can write a Python layer that does the interchange. So you do a diffusion step, and then you do a material exchange step. But we'd have to think a little bit about how to implement those.
Yeah. So the signal propagation is induced by calcium-induced calcium release, and they called the model is called the fire diffuse fire. So is that the pump, the channel you said that requires activation?
Well, so integrating fire models are possible. I'm thinking more really at the boundaries of cells.
Yep.
So for example, in root growth, some of the channels at the root boundaries are directional. That they have a preferential direction of transport.
Yeah. We will give it a direction. We may just do a one direction propagation. Yep.
And so if you want to do that, you have to implement that in some way, because diffusion intrinsically is bidirectional.
Right. Understood.
So if you want the channel to only allow flow in one direction, you have to figure out a way to make that happen. And it's not impossible to do it, but it does require a little bit of thinking about how to implement it. It's not something that's a primitive in CompuCell.
Yep. Okay. Yeah. I will have that in my mind.
Right.
Yeah. But these are great ideas and suggestions.
Right.
Yep.
And we'll get to diffusion and implementing diffusion probably in about 2 weeks, I'd say. It'll be a little bit. It'll be a week or two before we get there, but we'll see how to do that. Okay, great. But that's a great problem. And then if you want to show that, if you want next week to show an image or two from that paper and some equations from that paper and discuss them, that would be fine.
Yep. I can do that. Yeah, Jess and I think we can both work on this project. Yep.
Great. That would be good.
Thank you so much.
Great. And I guess Shelley? Okay. All right. So let's come back to the basics for the moment. I just want to review some of the things we went over. And you'll find that when I do classes, I will have a lot of slides which are in the form of last time. And occasionally these slides will have additional clarification or additional information. Sometimes they will just be there to remind you of things that we did. And they're also there to give you the opportunity to say, gee, you covered this last week and it didn't make sense to me, or it came up in the homework, I didn't know what to do with it, or I had a problem computationally with it. So when you see a series of last time slides, I typically will skip over them pretty fast, but they're an opportunity for people to raise issues that might not have been obvious, because typically you'll have we'll cover the material in class, then you'll have a homework assignment on it. And so if there was something that was unclear in class or that wasn't covered that you needed for the homework, this is an opportunity then to come back and say, hey, can you go into this in more detail? So one of the things that obviously I'm having trouble with at the moment, since I can't get into NanoHub, was how to upload and download files to NanoHub. Just making sure that people are able to do that if you're using the NanoHub deployment. And again, we had to use this Jupyter Notebook auxiliary application to do that. Then we started talking about CompuCell models. And the first thing that we discussed was the fact that CompuCell has a lattice in which cells live. And that lattice can be either square or hexagonal. And so far we haven't used a hexagonal lattice, but we can do that. Actually, it's something we could do today. I didn't write an exercise with it, but it takes one line of code to put in hexagonal rather than square for the lattice. That boundaries can be periodic. We have to specify how big our simulation is. And the thing that was perhaps the most unexpected, if you haven't worked in this domain before, is the idea that there's an intrinsic range of interaction, that you don't necessarily only have nearest neighbor interactions. And that's going to come up repeatedly during this class. And I want to remind us of that. In general, these kinds of lattice methods have limitations because you have to define the space you're going to work in. Although even off-lattice methods tend to become lattice-based when you talk about diffusion fields. And so this is a rather broad problem that you run into in a lot of cases. We also, and this is a very busy slide that tries to encompass too much material, was we started talking about cells, how we describe their behaviors and interactions, and what the dynamics for cells are. And we'll come back to some of these things again, but this is a summary slide. The basic concept of cells is that they're cell objects. Those typically are called generalized cells because they represent volumes of material, which could be real cells or could be non-cellular materials. The key thing that is specific to CompuCell, or these so-called CPM or GGH methods, is that every cell object has an index, an ID, typically given by sigma as the variable name, which is simply a number, so that cell number 1 has number 1, cell number 2 has cell number 2, and so on. And each domain in the lattice that has index number 97 is part of cell 97. That doesn't say anything about whether those pixels or voxels are contiguous to each other, or whether that organization makes sense as a cell. Every cell object by default has a type. Usually give it tau as the variable name for the type. We've already created in our simulation something called my cell or cell. It's a type name. By default, all simulations have an object of called cell of type medium. And that cell of type medium has slightly special properties which can be sometimes rather annoying. And we'll run into some of those issues today. Because we have voxels on a lattice, automatically cells have a volume, the number of lattice sites that are occupied. Surface is a little bit more problematic on a lattice, and we're going to find that the surface area of a cell is going to depend on the lattice type, whether it's square or hexagonal, and on the interaction range. And so when we specify surface area, we'll have to specify a range parameter, which might not be an obvious thing to do. In reality, we don't usually include range when we specify surface area. We have this idea of specifying what the cells are going to do in terms of these effective energies. Those will give rise to forces. And there's this modified metropolis dynamics where this pattern changes by attempting to move voxels at boundaries and accepting moves that reduce the pattern energy with probability 1, accepting moves that increase the pattern energy with an exponentially decreasing probability based on the energy cost. And again, this introduces just the way the range is introduced as a parameter you might not think about for describing surface area. This fluctuation amplitude T, which scales the energies fluctuations, is something that comes in here that one might not expect. And we're going to have to learn how to deal with that. I also mentioned that these are constructive models, so in general, nothing exists unless we assert it. We have to say there's a cell lattice to put things in. It's not there. We don't have cell types unless we assert them. We don't have cells unless we create them. And the cells don't have any properties or behaviors unless we assert them. And again, this is not problematic in practice, but occasionally somebody will forget to define something which is obviously a property of the cell, and the cell will not have that property. So it's something that we need to watch out for. Coming back to this idea of specifying a series of cell behaviors in terms of effective energies, this is something that we're not, in general, I think, used to doing. And I've tried to edit this slide a little bit from the way it showed last week to try to make this clearer. If I look at this cell as a picture now, as a snapshot, it has a volume. It's occupying a certain number of voxels. If I took that initial condition and ran it in the simulation with no effective energy associated with volume, what I would find is that those voxels would disappear. The cell would disappear. And so I need to have something that maintains the cell volume. And we'll call that a volume energy or a volume constraint. Similarly, if I don't specify what the surface area of the cell is, the surface area can fluctuate. And so if I want to maintain the surface area to be something, I will need to use what I will call surface area constraint. If I want the cell to be elongated in a particular direction, I'll use something that maintains the aspect ratio of the cell. And there are going to be other energy terms that will do other things. In particular, we've talked a little bit about contact energy, which we looked at last week. One of the things that we often will do, which we'll need to wait a week or so for, is talk about chemotaxis, cells moving in response to chemical fields. That would be another energy term, effective energy term. Sometimes we want to put explicit forces on cells. We want them to move in a particular way. Those will be effective energy terms, and so on. And so again, a big part of our simulation will be defining an effective energy, which will be a sum of a bunch of terms, each one of which describes some microscopic or simpler property of the cell or behavior of the cell. We talked about the fact that many of these energy effect. Josh, question.
Yeah, could you go back to the last slide really quick?
Yeah.
So I kind of ran into this when I was working on homework 2 regarding the surface area. So like in some of the simulations you had us do, initially the cell looked like that, but after, you know, a couple hundred Monte Carlo steps, the borders were like really wiggly and stuff like that. Is the surface area in effect increasing, or how does like, I don't understand how that works.
Well, so if I don't constrain the surface area, so if I don't put a constraint on the surface area, then, and there's no contact energy, then creating additional surface doesn't cost anything. And so this picture, having all the voxels spread out throughout the lattice as dust, have the same energy. And so, in fact, you can have cells fall apart if you have a volume constraint, and then we'll do this as an exercise, but it's a homework exercise, but we'll also do it in class. If you have a cell with a volume constraint and nothing else, it will turn into dust. So, and that dust has a high surface area because there's no penalty for that. So what is a little special about surface area is that having a contact energy and a surface area constraint, those two things are covering similar but not quite identical concepts.
Okay.
And so if you want to implement those two things together, there's a little bit of a play between the two. But absolutely, you're right. That's the case. And we'll do so. And that was why there was that homework exercise where we counted the number of pixels, what the surface area was of a cell, to get a sense of how it behaves as you change the shape. So, good question. So, again, when we're going to implement some of these behaviors, we'll often use the form of a constraint. A constraint has this very generalized form of actual value of some property of an object minus the target value. And we typically take the difference squared. And that gives us what's called an elastic constraint, parabolic constraint. And a constraint is associated with a constraint force that pushes the configuration back towards this 0 point. That is where the object property and the target property are equal to each other. And what's slightly magical about constraints is that we don't have to say how to do it. Any configuration will be pushed towards satisfying the constraint. We don't have to specify what direction we have to push in. That's automatically generated by the mathematics of the system. And that's one of the reasons that these energy-based methods are sometimes more convenient than force-based methods as a physicist. So if we have a volume constraint, this is basically the equivalent of the ideal gas law. Think of a balloon full of gas. That balloon will have an equilibrium volume. If we compress it, we have to push on it. If we want to expand it, we have to pull on it. That expansion or compression is related to the pressure. And the pressure then is the difference between the actual volume and the target volume. And there's this factor lambda, which is the strength of the constraint. The bigger lambda is, the more the system pushes against us if we move away from satisfying the constraint. Again, that has the slightly awkward terminology of inverse compressibility when we're talking about a gas. has a nicer name, which is Young's modulus when we're talking about a solid material. And so every energy functional is associated with a force. In this case, the volume constraint gives rise to a pressure. The surface area constraint will give rise to surface tension. And for a quadratic constraint, the associated force is linear in the divergence between the actual and the target value, which is why it has a simple form. And so the force is here -2 because it's squared here, so we get a factor of 2. And here, actually, I've put a minus sign. The minus or plus is a matter of convention. 2 times lambda times the difference between the actual and the target. And that's going to be something we'll run into repeatedly as we go through the class. Again, I'm just going over this because this abstract idea of a constraint can be a bit slippery when we work with something like volume and see how it works. It's better behaved. But this is, again, the ideal gas law in action.
Is it possible to use those types of constraints to keep a cell in one spot?
So you could certainly do that. You can do it in a number of ways. One of which would be to write a constraint that says, I have an energy cost associated with the cell moving away from where it is. And in principle, I can write a constraint that does an arbitrary thing. I want the cell to move 3 microns in the z direction, followed by 2 microns in the x direction, and so on. It's not going to be very pretty to write, but I can write an energy functional that will do that. In CompuCell, there's a concept of a link, which is essentially a spring. And I can tether that spring somewhere. I can anchor it somewhere in space. I can put it at one end of it anywhere I want. And the other end I can attach, and I have to attach it to the center of mass of an object. So I could attach it to the center of mass of a cell. And so I could create a link that tethers the place I want the cell to be to the center of mass of the cell. And then if the cell moves away, there'll be a restoring force pulling the cell back. And that's probably the most elegant way to implement what you just talked about. And then I have an option. If I use a classic Hooke's law spring, that has that linear force in the length, or quadratic energy in the length. But biologically, some kinds of tether don't have that behavior. For example, Filopodia pull cells on cells or cells on substrates, but the force they exert is typically independent of the length of the Filopodium. And so in that case, I'd probably write that the force was the absolute value of the length rather than the length squared, so that the force was constant as I changed the length. But that's a great question. Yes, absolutely, you can do that. And we've definitely had, I don't know whether we have any examples in the slide decks that I've got at the moment, but I had a visitor from China last year who was working on doing simulations of SU8 nano-fabricated devices. So she was building little pillars of elastic material, and she had her cells crawling on top of those elastic pillars. And we implemented those pillars as little pyramids of links, where if you displaced the top, you changed the lengths of the pillars, and that created a restoring force. So that's an example where the quote cell in that case, which represented the pillar, wasn't representing a biological cell, it was representing a volume of elastic material instead. Really, the difference between a cell and a non-living material in the modeling framework is determined by what attributes you give it. Basically here, this is a method that allows us to model some volume of material. And then we have to decide what makes it cell-like or not cell-like. Good point. So if we have a bunch of energy functionals or effective energies for volume, surface area, length, contact energy, and so on, each one of these independently creates a force on our cells. And the system will try to minimize the energy, which is equivalent to saying it will try to satisfy all of the constraints. But it can't actually typically satisfy all of the constraints simultaneously. If I said that my target volume for my cell is 0, actually I better be careful because I'll give one that it can be satisfied. If my target volume for the cell is 100 and my target surface area for the cell is 0, I can't have a cell that has a finite volume and a 0 surface area. And so what I'm going to have then are incompatible constraints, and the system will arrange to balance those two. It won't have the volume constraint perfectly satisfied. It won't have the surface area constraint perfectly satisfied. It'll have to come to some kind of accommodation. And that compromise is going to be governed by the strength of those constraints. If I make the constraint amplitude lambda for volume very strong, then when I run the simulation, the actual volume will be close to its target, but the other factors may be very far from their targets. If I make the lambda for surface very large, then the surface area will be close to its target, but the other things may be far away. Typically, what I want is to adjust those lambdas so all of those factors are at play. If I make one lambda very big, I might as well leave all the other terms out because they're not doing anything. And so one of the tricks in this, and one can do some of this with a pencil and paper doing the calculation. Some of it one has to learn a little bit of intuition about, or learn how to recognize it, is that when we are adjusting our parameters, we often need to adjust those lambdas so that all of those energy functionals are contributing to the behavior at the same time. And typically what matters is, it's not the absolute value of the energy functional that matters, it's the changes, although they're typically on the order of the value. And so what's going to matter is, what's the typical change in energy due to a change of volume, to change of surface, and so on, normalizing that by lambda. If those are all of roughly the same order of magnitude, then the simulation will do what we might expect. If they're not, then we'll find that it doesn't. Well, we talked a little bit about how these ideas correspond to the code in CC3D-ML. First, we were listing the types of cells, and this concept of cell type is built into CompuCell in some fundamental way. That medium cell of type 0 we're always going to have, and we're going to find that we have to do a number of workarounds for that. There was maybe a mistake early on where medium is defined as a non-cell type, and so it doesn't have some of the attributes other cell types do. And so very often when we iterate over things, we're going to have to check that things aren't medium, because if we do things to the medium, they don't have those properties. And Python will complain. If we are trying to do something like specifying target volume or volume constraint, our equation, lambda volume V actual minus V target, if I look at the plugin, I have volume here. I have to say what kind of cell this applies to. Lambda volume here from the equation, target volume here from the equation. And so there's a pretty direct mapping from the equation to declaration in markup language. Same thing for surface area here. Surface energy, cell type it applies to, lambda surface, target surface. We'll find that the surface plugin also allows us to specify the interaction range over which that calculation is done. So I'm going to just very quickly flash the homework problems and ask people if they were able to do them. If they were, I'll give people the opportunity to show their result or comment on the result. If they're questions, I've got a solution worked, but I don't want to take a lot of time going over problems that everybody already did and didn't have trouble with. So the first homework problem was suppose that we only had a system with a volume constraint, and for purposes of definiteness, we gave a target volume of 25, lambda volume of 2, and I gave a picture, and I asked what was the effective energy of the image. Does anybody have a result for that? Are there any questions? Did anybody have any issues solving this problem? Everybody got it? If you didn't have any issues, what was the result?
I think I put down 32 for that one. Let me flip back. Yeah.
That's fine. Okay. And then there was a question thinking about actually the dynamics, which is what was a single voxel change that would reduce the volume constraint energy. In this case, the volume is 22, which is less than the target, so adding 1 voxel would reduce the pattern energy. What was the lattice configuration that had 0 volume constraint? Well, any configuration that had 25 voxels in it would match. And if the target volume were 15, now I'd be too big, so I'd lower my energy by getting rid of voxels, and everything else would be the same. 32 is what I got. So 1B added a surface constraint, and the purpose of this was to think about the fact that you couldn't satisfy the volume and the surface constraint at the same time necessarily. And what you'll find is that actually there's a reasonable range of target volume. For given target volume, there's a reasonable range of target surfaces for which you can satisfy both constraints. If the target volume is too big compared to the target surface, you can never satisfy both. And similarly, if the target surface is too big compared to the volume, you can't satisfy both. And so there's a range over which both can be satisfied, and then if you make them too far out of whack, you can't. So does anybody have any, what did somebody get for the total effective energy of the image? Somebody volunteer.
This one was a little bit tricky at the beginning. I got it wrong at first because I was assuming that the surface was also done by the number of voxels, but then I read the material again and I saw that it's like actually the perimeter voxels. So I got 15 for the perimeter. I can share my screen if that's okay with you.
Sure.
Yeah. So this was the solution that I came to. One is 75 for the volume, and the other one is 200 for the surface, and the total is 275. But I got it tricked me for a second. I had to revisit the material and make sure that the surface was not equally to the volume.
I think you had in problem, it's 1B, right? I think the target surface is 13 and not 25, because I got something different, but
Yeah, same.
I saw in your calculation you took the target surface minus 25 instead of 13.
Yeah, my mistake. Yes, you're completely right. It's 13 and I did 25.
Okay, yeah, because I got 750 for the total of volume and surface, so I don't know if anybody else got that.
Yeah, I'm with you.
But I think one of the things that makes this one complicated is that while adding 1 voxel of red or taking 1 voxel of red away changes the volume in a well-defined way, where you put it is going to change the surface area differently. If I make this voxel here, white voxel here that's in a notch red, I get rid of 3 units of surface and I add 1, so I reduce the surface area by 2. If I added a voxel sitting out here in the middle of nowhere, I'd add 4 units of surface for a voxel. So adding 1 voxel to this cell, making the cell bigger by 1 in volume, could reduce the volume by, reduce the surface area by 2 or increase it by 4. And so where you put it makes a difference. And so the point of this exercise was really to think about the fact that these constraints can conflict, and that something that moves one constraint in a simple way might move the other constraint in a more complicated way. And again, go ahead.
I know that we on the exercise was supposed to select the exact one we wanted, and I know that there was like the best choice, one that we could take away, and it also increased twice the surface constraint. But this actually happened randomly, right? You don't have the power to choose, right? The function doesn't have the power to choose.
Right. In principle, though, the function, the algorithm we do will explore every possibility. The thing is that it doesn't explore them all at once. It doesn't look at every possibility and find the best one. It will try one at random, accept it or reject it. It'll try another one at random. And because they're sequential, the situation that it finds itself in after one change is not the one that it started with. And in fact, the choice, the most important thing in this particular algorithm, this Potts algorithm, this modified metropolis algorithm, is picking the sites randomly. The random number generator that picks which locations you visit has to be very high quality. If you use a crummy random number generator like RAND in C++ or Fortran, the correlations in that random number generator mean that this simulation method doesn't work. And so we have to do some work to make sure that the choice of lattice sites for updates is actually picked very randomly.
Can I ask a more logistical question really quick? So I actually hesitated on submitting my answers yet because what happened was that I worked out a lot of the math by hand, and I had a digital PDF of it. And then I had the typed out stuff for the simulation questions, and I realized I wasn't sure what formatting requirements there were for submissions of assignments, if there were any.
So whatever minimizes the pain to you. The reason I like to use, the reason I ask you to submit through Canvas is because that way I don't lose things. So I'm less likely to lose things. However, occasionally Canvas will be a pain, and it'll say you have to, I won't let you upload a zip, or you want to have multiple files, these kinds of things. As far as handwritten material goes, if you want to take a snapshot of it with your cell phone using card scan or whatever if the phone app is, and turn it into a PDF, don't feel that you have to type everything. Just do check that you can read it. In other words, if I get an image where I can't see it, I can't comment on it.
No, yeah, that makes sense. I was more concerned that it meant that some of my stuff was out of order because I did 1 by hand and 2, and then I did 3 and 4 on the computer, and then I did 5 was a mix of computer and by hand.
Well, so then you could either, if you're feeling generous and have time, you can go into Acrobat and shuffle the pages so that it's in order, or if you're in a hurry, upload it the way you have it, but please put a note explaining to me what you've done so that I know what to look for.
Okay, sounds good. I'll go ahead and rearrange it.
Since I don't have a grader for the class, if you save me time, I'm grateful. But I also know that you have a lot of things on your plate, and I don't want you to be spending a huge amount of time. I mean, I've had students who typed everything beautifully in LaTeX for their homeworks, and I kept saying, it's okay. You can write the equations by hand and take a picture of them. But if you want to type everything beautifully in LaTeX, I'm not going to complain about it, but it's certainly not required. As long as I can read what you've done and understand what you've done, that's all that's necessary. It doesn't have the beauty of the presentation is not so important. Now, for the final project, where you're presenting the material to some outside user, there I'm not going to put there are not a lot of marks given for how it looks, but it has to be clear enough that somebody who's not an expert can understand it. And so in that case, spending a little time on the aesthetics of the presentation is important. But for the homeworks, as long as I can read it, understand your thinking, that's all that matters. Don't take more time than you need. Okay. So here, sorry, go ahead.
I had a theoretical question really quick, just trying to understand the idea of the constraints between volume and surface area. Theoretically, if we had a target volume of 1 and a target surface area of, say, infinity, would the most ideal case be the unit circle? Or
well, so if the target volume were infinity and the target surface area were 1, your ideal case would be a circle.
Okay.
Or actually, because we're on a lattice, and this is where the fact that you're on a lattice is a pain. If you have nearest neighbor interactions and you have and you're on a square lattice, the minimal surface area is a square rather than a circle, which is not a very good approximation to a circle.
That's why I specified theoretically. So
right.
It doesn't have to be on a lattice.
Right. So in the real world, if you have a large volume and a small target surface area, effectively you have something like a beach ball that's inflated very much, or a basketball, and it'll be a sphere or a circle.
Mm-hmm.
In our world, because we're on the lattice, it'll be a square if you're nearest neighbor. And if you did the same thing, and this is actually an exercise we may or may not get to today. It's in the list of exercises, but I don't know whether we'll get to it. If you change the interaction range, when you have a fixed volume and the target surface is too small, the shape will change as you go from nearest neighbor to second neighbor to third neighbor to fourth neighbor.
Mm-hmm.
But for nearest neighbor, it's a square. If I have the target volume being small and the target surface being large, then effectively for a given volume, the target surface is biggest if I have dust, if I put my voxels separated from each other.
Okay.
And there'll be a limit because I can't have a surface area bigger than the dust surface area. So if I had, say, 4 voxels and I have nearest neighbor interactions, the biggest surface area those can have would be 16.
Okay.
Or 4 on each one.
Mm-hmm.
And so I guess it was worth maybe going over these homework problems a little bit, because these are issues, and I think they're not trivial. Thinking about these relationships between surface and area, especially on a lattice, is tricky. And normally we try to set the configuration, the model configuration up so you don't run into these pathologies. But when you do run into them, it's very helpful to have done these exercises, because then you can have an intuition of, gee, I made the target volume too big. Gee, I made the lambda volume too small. And so when you see the pathology, you then have an idea of what went wrong in the definition of the simulation. So in this case, the target volume was, I said, 15. The actual volume was 20. The target surface was 13, and the actual surface was 28. And so I win for both volume and surface by eliminating red. If I had exactly 15 voxels, so I'm satisfied my volume constraint. If I had 16, that would be 4 by 4. And so the smallest surface area I can get would be a square of 4 by 4 with one corner chopped out of it. And it winds up, if I do that, my surface area is 16. rather than 13. So the smallest area, the smallest energy I can possibly get is 27. That one I can do by hand. But, and again, thinking about the continuous case, I thought about giving that exercise, actually. I thought about giving this exact exercise for a sphere, for an off-lattice case. And the problem with doing that and asking what is the radius that you get under these circumstances is that you get a fourth order equation, because you have V minus V target squared. V is proportional to the square of the radius in 2 dimensions. And so you have V R squared squared, so you have R to the 4th. And so unless you set V target or S target to 0, you get a fourth order equation. It's not that it's hard to solve numerically, but analytically it's not soluble. And so you have it's not transcendental, it's just a mess analytically. Joel, did you have a question?
No, it was just that I think you were showing something on your screen, but we cannot see. You were like talking about the image, and like if I take this out, and I could not see, at least on my.
Oh my goodness! So what? Well, how long has my screen share not been on?
Since I stopped my share, I guess.
So I did the
Sorry.
share and it must have disappeared. So please tell me, because I've been carefully walking you through. So you didn't see any of these slides?
We saw the first question, but not the second one. No, we saw those. As soon as you start talking about the exercise, yeah.
Yeah, I think
After
we
that
saw up through 1B, we saw the slide,
Okay.
like the first part of 1B.
Okay.
We saw the slides for.
Okay. Because I have had an issue with Zoom in the past 2 weeks, occasionally knocking me out of screen share and or a recording and or subtitles. And I'm not quite sure. It's not that Zoom throws an error and I know something has happened. So if I'm talking as if I'm screen sharing and I'm not, please tell me right away. I'm sorry. I appreciate your patience. And we could say, well, this wouldn't happen in class. But in class, I would still be displaying something, and I'd be looking at my laptop, not at the screen. And it's happened to me in class, too. So, and even in class, people sometimes say, well, gee, there's a blank screen talking in front of a blank screen. So, oh, well. So please. So here was the comment where I did the calculation by hand. The actual energy here was 555 in my calculation. The best we could possibly do would be a square of 4x4 with one corner notch cut out. That would have an energy of 27. Okay. We talked about this dynamics. The key point about the dynamics is that in the micro world of cells, unless we're talking about things like blood flow, which do have an inertia, at least in larger blood vessels, we're overdamped. If we don't push on things, they don't move. And so the basic result is that the velocity of something and the force are linear related to each other, so there's no Newtonian acceleration. F equals drag times V. And we have this specific stochastic algorithm that we call modified metropolis dynamics. And exactly where that comes from and why is in the papers that I sort of background reading I gave you. It's not that important. But the key thing about it is that it does give you a velocity that's proportional to the force, provided that the forces aren't too big. And the forces not being too big, they're always rescaled by this fluctuation amplitude T. If the change in energy for a 1 voxel change divided by T is very large, on the order of 1, then this linearity fails. You could say, well, why don't you just make the probability linear in the energy instead of exponential energy. And you can do that, and actually it's possible to do that in CompuCell. The simulations run a little bit faster. Things don't change dramatically. It does have some mathematical awkwardness, namely that the probabilities aren't differentiable at the point where delta H is 0. There's a kink in the probability function. But we'll see that a little bit later in the slides that I've been using from Giulio. He did some very nice analysis. But this stochastic updating algorithm, again, takes a little bit of getting used to, and it can have its own pathologies. For people who are physicists or mathematicians, I don't think I have any real well, maybe some mathematicians do. There's a basic relationship which says that energies that are derived from forces that are derived from a potential can't be rotational. You can't have a non-zero curl for force derived from a potential. It's a basic mathematical law. In the world that we live in, you can have forces that have non-zero rotational effect from a potential. And the reason for that is that you only evaluate the energy functional at the change in energy functional at one point at a time. You're not evaluating it everywhere at the same time. And so you actually then break this rule about the restrictions on forces derived from potentials. The cost of that is that you lose simultaneity. You don't know when things happen over short time scales because you're doing updates stochastically in different places. And so asking, did this thing over here move before this thing over there, doesn't make sense over a time scale of less than a Monte Carlo step. And so there's no free lunch. In this case, you get this violation of what seems to be a fundamental mathematical law. But the cost of that is that you don't know what orders things happen on over very short time scales. That's probably not of interest to anybody who's not a physicist. But back when we started developing these methodologies years ago, physicists would say, but you can't do that. It breaks a fundamental mathematical rule. And so I had to explain why we could get away with it. Those kind of uncertainty relations, physicists love uncertainty relations. And that's one of them. Okay, so the first thing that we said, the next homework problem was one which somebody already asked about, which was, what happens if we have a cell with only a volume constraint and nothing else? What happened when people ran that? Somebody? Nobody's speaking.
It looked like dust.
It turned into dust, yeah. It'll turn into dust. The volume is constrained, but nothing else about the cell is. Surfaces. Okay? And then I had these examples which were trying to explore this region where you had too much surface to volume or too much volume to surface. And there was this whole list of possibilities. I don't want to go through all of the details here, but I hope now, having had this discussion about there's a range over which you can satisfy the volume and the surface area constraints together. But if the volume is too big relative to surface, you can't. If the surface is too big relative to volume, you can't. That explains why I was saying high target volume, high surface, and so on. And then when you change the lambdas, you can switch. If you can't satisfy both, by changing the lambdas, you can decide, or by closer to satisfying one or the other.
Really quick, could you define high and low in this context? Because I didn't really know what order of magnitude, because I remember I actually counted the number of voxels and it was like something around 164, but that was after I did the simulations, and I had, for my high target volume, it was 100 and my low was 10. So I don't know if that, since my high never really went over, I don't know.
Right. So let's suppose, let's do the exercise I think you already just alluded to. If I wanted, in the real world, if I suppose I'm in 2 dimensions, and I have my I want a perimeter, a surface area, and I have a lot of volume and a small surface. The most efficient thing I can have is a circle, a disk.
Mm-hmm.
So the volume is pi r squared, and the surface is 2 pi r. So if the target volume is 100 and the perimeter that I'm trying to get is 1, I can't satisfy that. I'm going to be under tension. That's like blowing a lot of air into my beach ball, so it'll be under a lot of tension. So in the case of nearest neighbor surface area counting, then the best I can do is a square. So suppose I have a volume of 16, that would be 4 by 4. That gives me a surface area of 4, 8, 16 of 16 as well. If I make the target surface of a volume of 16 less than 16, I can't satisfy it. Mm-hmm. On the other hand, there's something else, which is dust. In the real world, I can make my dust as fine as I want and have as much surface area as I want. In this, I can't make a pixel less than the size of a pixel. So the biggest target for a volume of 16, the biggest surface area I could have would be if I took each voxel, moved it away from each other. Each one would have a surface area of 4. So the biggest surface I could have would be 4 times 16. So 64. So if I start with a volume of 16, the biggest possible surface area for that is 64. The smallest possible surface area for that is 16. So within a target surface of 16 to 64, I can satisfy both constraints simultaneously. If I go outside that range, I can't. And so when I say high and low, that's what I'm talking about. Am I within those constraints? And if not, can I satisfy both simultaneously? And if not, which one is too big compared to the other? Okay. And so that was a bit of a challenge problem. I recognize that when I asked that question, it required thought. And the goal of sometimes of these questions is sometimes they're hard. They look simple. Asking a question, what's a high target volume or hard surface? It looks like a simple question. And the goal is to inspire people to think about it and ask a question like the one you just asked. Did that clarify things? And I am screen sharing now, is that right?
Yes and yes.
Yeah, okay. And then the same thing with the lambdas. If lambda volume is much bigger than lambda surface, I'll satisfy the volume constraint and the surface area constraint won't matter. If lambda surface is much bigger than lambda volume, I'll satisfy the surface constraint and the volume constraint won't matter. If target volume is very big compared to surface, the cells are floppy or fall apart into dust. If target volume is much less than target surface, I'll get stiff, round cells. It's golf balls. So that's good. Another thing that we could think about is what if we see a behavior in our simulations, are things behaving reasonably or not? And this is a simulation we did last time. And in the left-hand case, I have a cell that's crawling by itself. The cell is amoeboid. It's moving freely. And I would, looking at that, say, probably that cell is behaving in a reasonable way, depending on what I'm trying to model. If I look on the one on the right, the cell is splitting up into separate domains. It's falling apart. It has a lot of isolated voxels. And so in that case, I would be in a situation fundamentally where the fluctuations in my system are too big compared to the energy constraints that I have. Similarly, on the one on the left, on the right, I have a cell sorting simulation. In the left-hand one of these two on the right. My cells are moving freely. They're relatively round. The boundaries between them are relatively smooth. And I would say that this is a system that is generally behaving the way cells might behave in real world. If I look at this one here on the far right, the green cells are square and aren't moving very much. That is that the fluctuations are too small for them to behave appropriately. And similarly, in the middle, in the blue, the boundaries between the blue cells are falling apart completely. The blue cells are mixing with each other. And that means that the fluctuations are too big compared to the energies of that system. So in this case, I have one kind of cell, green, where the fluctuations are the energies are too big compared to the fluctuation, and one blue where the energies are too small compared to the fluctuation. So again, these are pathologies, cells falling apart, cells freezing and lining up with the lattice, cells mixing with each other. These are all pathologies that you can run into with this modeling method. Actually, all of these things do occur in the real world as well, but most of the time they're occurring under special conditions. They're not the normal things you want cells to do. And so the goal here is to think about, when you see these kinds of pathology, what's going on. If this is the case, the fluctuations are too big compared to the surface and volume constraints. In this case, if they're square, the fluctuations are too small compared to the surface and volume constraints. Now, in the case of this one on the right, where I have blue and green, and I simultaneously have some cells that are where the fluctuations are too small and some where they're too big, in that case, I can't use that T parameter because that has to change for every cell at the same time. Making it bigger, making T bigger, will make the green better, but make the blue worse. Making it smaller will make the blue better, but make the green worse. In that case, I have to change the parameters of my simulation of the cell types because it's telling me that I picked the values improperly. And so there's some basic things that you should look for. Cells should stay more or less connected. Having an occasional pixel fall off is fine, but they shouldn't split in two, unless you're simulating blabbing, in which case it's a different problem. Domain boundaries should be fluid, but not crumpled. Cells should be more or less rounded, not squared off with corners. Now, I'm not saying that those things don't occur in biology. Plants can have square cells because they're under a lot of tension and pressure and they have rigid walls. Cells can split and merge under certain circumstances. But you want those things to be things that you did intentionally, not things that were accidents of the simulation methodology. Okay. If the fluctuations are too small compared to the effective energies, cells won't move. Cells will line up with the lattice directions, and you'll see facets, these corners. If the fluctuations are too big compared to the effective energies, cells will split into multiple domains. You'll see lots of stray voxels, and you'll see the crumpling of boundaries. And so we can have a little bit of a list of pathologies, and each one of those pathologies will correspond to whether the fluctuations are too big or too small. Okay, then we started out doing this very simple simulation of a single cell type, and we're playing with contact energy. The key thing to remember always is that when you're talking about things sticking to each other, higher energy means they stick less. And it's really amazingly difficult to get that into my head. Everyone feels higher energy should be better, and higher energy is worse. And so it's something we have to remember. The contact energy, again, we tend to specify in terms of cell type pairs. So there'll be a JAA. That'll be the energy per unit area, the surface between cell of type A and type A, of A and B, A and C, and so on. And again, remember, larger energies are less adhesive. And we've just done all these exercises exploring this. We were able to do steering, that is, we were able to change these energies as the simulation ran, which was very convenient. And you'll notice here in the contact energy plugin, line 41, neighbor order is 4. So there is this neighbor order parameter, which is telling you what range you're calculating the surface areas over. The one thing to remember when you're doing steering by hand in Player is that if it looks like 10.0 and you type it in, you have to type 11.0, not 11. And similarly, if it's 4, you've got to type 5, not 5.0. Only the parameters that are specified in the XML are going to be available in that steering window. And when we use Python, sometimes that'll be a little bit of an annoyance, although there are ways to steer Python parameters that we'll talk about later in the class. The other thing that's a little bit annoying is that CC3D doesn't log the changes that you made. And I've been saying for years that we should add a log function. If somebody wants to add that function in a class project, that would be great. It's easy to do. I don't know why we don't write out a log file. And then we looked at our basic results. Our initial default situation gave us a slightly rounded aggregate. The cells were basically well behaved. There were some bumps on the aggregate. We tried increasing the cell medium contact energy, and the aggregate became more compact and rounded up. When we decreased the cell medium contact energy, the cells began to almost fall apart. The aggregate began to become a little bit dispersed. When we increased the cell medium contact energy to be less than 1/2 of the cell-cell contact energy, and we can define something called surface tension that's exactly that, the difference between those two numbers, then the cells disperse through the medium. So this would be the multicellular analog of the pixels dispersing for a single cell. So now my suggestion is that we come back to this, and I'm not sure what to do because let me see if I can get Twit it running. Let's see if I can get this to be visible. If I can't use NanoHub to display, I'm going to have to do a little bit of playing around here to make sure that I can do a split screen. I'd like to go from where we ended the last time and try exploring some of these changes in energies. So it looks like we're halfway through the class. Why don't we take a 5-minute break now? Who is able? Is there anybody who is able? Is everybody able to run CompuCell in some form? So either you can run it locally or you can run it on NanoHub. Okay. So the one problem that I have sometimes with CompuCell on Zoom is that if I screen share Player, for some reason the font sizes in not Player. If I screen share TwitIt, for some reason the font sizes in TwitIt get messed up. And so one of the reasons I prefer to screen share with NanoHub is that I don't have that problem with the fonts getting mixed up. But let me see. Give me 5 minutes. We'll come back at 6:45, and I will. By then, I hope I will have things working one way or the other. Okay, so the first exercise would be to come back. Do people remember how we did the simulation that we did before? Do people have it from last week? Okay. Let me see if I have it from last week. Okay, so everybody should have the simulation. And so before we were running this and we were changing the energy between the cells and the medium. And now what I'd like you to do is decrease the energy between the cells from 10 to 1 and run the simulation. And before you do it, maybe we should I'll ask you to think, what do you expect is going to happen when I change the energy? I'm going to be reducing the cell-cell energy. What do you expect to happen? Think about it for a minute.
Hey, wait, this is one of those trippy moments where this is one of those cases where energy is lower, right? So if the contact energy is lower, shouldn't that mean that they adhere more?
Okay. What else is going to happen?
Are the cells not going to keep a very uniform shape?
That's right. Because the surface, creating surface will change, will cost less. So let's try that. Why don't we all do that together? You can do it in the XML, or we can just do it with steering. I'm going to do it with steering. So let's do it together. And actually here I was supposed to reset this value to 10 before I did that. And so let's take the cell-cell contact energy and make it 1 instead of 10. Let's see what happens. The cells stay stuck together, but if I zoom in, their boundaries are getting quite rough. They haven't blown apart quite as much as they did with that other example that I showed. But you can see the cells are fluctuating a lot more. And I could, in principle, make this number even smaller. What if I made it 0.5? Now the boundaries are getting extremely fuzzy. Okay. So again, the tissue is also smoother. Notice that the shape of the tissue is much rounder. So I basically made the fish tissue more fluid-like. If I'm used to plants, I've gone in exactly the wrong direction. I've made my cells even more amoeboid and less rigid than they would be for plants. You'll also notice that this is on a square lattice. Notice that there's a little bit of a stop sign shape. There's a little bit of an octagonal shape here. And that's because even with a longer interaction range, especially at the top, it's hard not to line up a little bit with the lines. The bottom looks pretty good. Okay. So one of the things that we talked about was which is bigger, cell-cell or cell-medium contact energy. And before, when we made the cell-medium contact energy smaller than the cell-cell contact energy, we saw that the aggregate got loose, and eventually, when the cell-medium contact energy was less than half of the cell-cell contact energy. And the reason for that, a half, is a little tricky. It's because cell-medium, when we have cell-cell, we count the energy twice. We count the energy from cell 1 to cell 2 and from cell 2 to cell 1. When you have cell-medium, you only count the energy once. So there's a factor of 2. But in this case, when we change the cell-medium contact energy in the cells to be small, the cells dispersed. Now I want to go back and just ask the question, let's now make let's go back to 10 here for the moment, which was our reference simulation. This was our base simulation. And if I made cell medium contact energy 1, what's going to happen? Cell medium contact energy is 1, cell contact energy is 10. What's going to happen?
The cells will probably disperse into the medium.
Right. Okay, let's do that. They do. Okay. And now if I make cell contact energy 1 again, what's going to happen? Somebody guess? Think. What's going to happen?
They will start to clump on each other.
Right. Notice when I made the cell medium contact energy 1, the cells are very irregular individually. And I see here this cell split. I have stray pixels. And so let me do this. Let's all do this together. Let's make that 1. They're clumping up, but the cells still have very irregular shapes. So 1 and 1 and 10 and 10 are both the same in terms of the clustering of the cells, but the shapes of the cells are different. One case the cells are irregular, the other they aren't. And so the ratio of the two matters, because if the cell medium contact energy is less than a half of the cell contact energy, you disperse. If it's bigger than a half, you coalesce. But the shapes of the cells and the shapes of the aggregate will depend on the absolute values as well. When I had cell medium contact energy large, I got a round aggregate. Here, the aggregate is very irregular. When cell contact energy is large, my cells are round or square. When it's small, I get irregular shaped cells. And so this is this idea of trying to get a sense of what are reasonable parameters. All of these things are only reasonable with respect to that fluctuation amplitude called the temperature. If I multiply the temperature by 10, I'd have to multiply all my other parameters by 10 to keep the simulation the same. Okay. So this was this question about why is the simulation result so different? This was everything is 10 and everything is 1. And I think we've addressed that. Are any questions about that, or are people comfortable with that? So this is something, again, that as you go forward, when you only have one cell type, it's easy to see these things. If you have 10 cell types in your simulation and one of them is misbehaving, it's not always so easy to catch. So that's why I want to spend a reasonable amount of time doing very simple things to get a sense of how this system behaves. Once we start doing complicated things, this is also a principle of modeling, which I think is not in that paper very well, which is when you build a complicated model, you should really build it one mechanism at a time. You put one thing in, you make sure that that works. You put one next thing in, you make sure that that works. Now, some of these models that we build are very complicated. They have many, many mechanisms happening simultaneously. And if you build it all at once and there's a problem, you don't know where the problem is. And it's very tempting to want to build the whole thing first. And I'm thinking about this specifically in the case of the dictyostelium simulation, where the student last year was very ambitious, very good, and they put all of the model together at once. And it didn't work. And figuring out where it didn't work was really a bear. And so I went back and rebuilt the model. Just have the cells, make sure the cells behave. Have the chemical oscillator, make sure it behaves. Have the diffusion of the chemical, make sure it behaves. Each one at a time. And then maybe when you put it together, it works. There's still no guarantee, but you're more likely to be able to catch your problems. And in experiment, whether it's biology or physics, you're always told vary one parameter at a time. Now, sometimes you can't. Sometimes things are intrinsically coupled, so it's not possible just to change one thing at a time. But when that is the case, it's much harder to debug your experiments. As somebody who spent most of his life as an experimentalist, I'm very aware of the problems with doing clean experiments. Okay. So if we think about these simulations and why they're so different, this is what's called the acceptance function. This is a plot of the probability if I make a change and the change reduces the pattern energy, I accept that change. If I make a change and I increase the pattern energy, I still may accept it, but the probability decreases exponentially with the cost, with the energy cost. And this is actually not a bad model of what happens when you have cytoskeletal fluctuations in cells. It's not perfect because the fluctuation spectrum isn't exactly Boltzmann, but that's the same. Okay. If my J medium cell and J cell is 10, the typical change when I add or subtract a pixel might be here, a larger energy. And that gives me some probability of making that change of 0.15. If my energies are smaller, here a factor of 10 off, the typical fluctuation energy will be a tenth as much. And that's going to push me up this exponential. And so the probability of making unfavorable moves is going to be not just 10 times bigger, but e to the 10 times bigger. It's much bigger. And the result of that is that I'm going to make, most of the time when I say, am I going to make this change? The answer is yes, even if it's unfavorable. Now, on average, I make it, unmake it, make it, and unmake it. The equilibrium configuration will be the same, but I'm going to be spending a lot of time basically going backwards and forwards randomly. And so that's really the situation that's going on here. That's why the energy scales matter. If I reduce the fluctuation amplitude by 10, why don't we try that? I think, does it work? Can we steer in the pot simulation, in the pots, or does that not work? We may have to do this in Twit. I'll try it, and if it doesn't work, then we'll come back. This fluctuation amplitude called temperature, the default here is 10. If I now make it 1, and I don't know if this is going to work, it did work. I should recover exactly what I had when I had the fluctuation amplitude be 10 and the energies be 10. Because the only thing that matters is that ratio. Did people try that? Can everybody try that and see what happens? You can play around here with the fluctuation amplitude and make the temperature 2. Fluctuates a bit more. It was 10 before. Too much. What if I made it 100? So this is this idea that the changes of energy have to be roughly on the order of magnitude of the fluctuation amplitude. We want them to be a little bit smaller than the fluctuation. I mean, bigger than the fluctuation amplitude. See, the cells are beginning to fall apart. But there's a pretty big range over which this is well behaved. So you don't have to get these things exactly right. You just have to be close. So the answer here was, if I make J medium my cell, J my cell 1 and temperature 1, and J medium my cell, J my cell 10 and temperature 10, do I get the same result? What was the answer? I showed you the answer. What was it that you do? So you can rescale everything by 10. Yeah. Okay. The other thing that we did with fragmentation, and we've already done this to some extent, was initially, I'm going to put things back the way they were. This is where we started. And I said that if I reduce the cell medium contact energy, then I'm going to get the tissue to fragment. And I did that, make cell medium contact energy 1, it fragments. I don't have that many parameters to play with. But what else could I do to make the system fragment? I said before, what matters is the ratio of cell medium to cell-cell contact energy. So instead of reducing the cell medium contact energy, what else could I do? Maybe it's so simple it sounds like a trick question. Somebody?
Making the cell energy higher?
Yeah. How much higher? You can try it. $15? What does that do? Try it. Things are getting a little bit looser. Like 20, factor of 2. Just at the boundary. 30. I get fragmentation. So again, the ratio matters. It's the ratio of those energies that matters. However, notice here, these cells are very round. In the case where I reduced the cell medium contact energy, I got fragmentation, but the cells had crinkly boundaries. Here, I have fragmentation, the cell boundaries are compact. And so you can compare that difference here. And so again, this is, in a sense, we're doing something very, very simple and maybe not so biological, although there are cells that are compact and have high turgor pressures, and there are cells that have a lot of medium that fluctuate a lot. So there is some range that happens in real cells. Which of these two simulations, and this is Julio's slide, which of these two methods would you prefer to do to model epithelial to mesenchymal transition? This is a question, essentially, of which of these behaviors is more biologically meaningful in this particular context. And if you haven't played with the cells, and I cut out a bunch of slides about EMT, so I didn't really cover it in detail. But somebody who has a biological background, I said something early on about epithelial cells tend to be columnar and have, if we look at them from the top, have relatively compact shapes. It's not true of all epithelia, but generally it's pretty true. Mesenchymal cells tend to be more disordered. And so, from my point of view, this left-hand one is probably a better representation of epithelial to mesenchymal transition, because we want the cells, when they become mesenchymal, to become more protrusive, have more irregularity in their shape, to move faster, and so on. I'm sure that we could find counterexamples to that, but that would be my instinct. So let's talk about cell shape a little bit. The things that we have to control cell shape in this simulation at the moment are very limited. We have two parameters, cell medium and cell energy. That's it. Real cells have incredible range of shapes. You have things like neurons, which have all of these ramifications, and where it's not even clear that what's happening to determine the shape at one end of the cell is sending a signal directly that changes the shape at the other end of the cell. Basically, different subregions of the cell are behaving effectively independent of each other. You have cells like fat cells that in some ways, although they're softer, behave a little bit like plant cells, because you have this fat globule in the middle of the cell that's not participating in the cytoplasm of the cell. You have macrophages and neutrophils that are very invasive and crawl around a lot. You have these epithelial cells that we've talked about a great deal. In the case of muscle cells, you have the complexity that the cells actually aggregate. They lose their cell-cell boundaries and merge together to form a syncytial structure. Erythrocytes, so red blood cells, have that classic cap shape that's so familiar, although when they're in sickle cell mode, they don't do that. And they're sort of a special case because they don't have nuclei. They lose their nuclei. And then you have specialized cells like sperm cells that swim in a particular way, and where almost all the cytoplasm of the cell's gone. So they're very, very different cell shapes. Here, we're only going to be able to talk about a small range of cells. The things that we're going to control here are not going to be so great. And partly this is because of the scale of the simulation. If I'm only putting 16 voxels into the cell, the range of shapes I could get with 16 voxels is limited. If I wanted to simulate the complex arborization of a neuron, I'd have to put thousands of voxels into each cell. You could do that, but then the number of cells I could simulate would be relatively limited. If I look at mesenchymal cells crawling around, they do have this very spiky sets of shapes. Those spikes are typically associated with what are called filopodia. They're particular kinds of actin protrusions in the cells. And so this kind of shape, I think, does suggest this bottom example more than the top one. So let's now do a simulation in which, in addition to the surface energy, we're going to control the surface area. And these things, as I mentioned, are related but not identical. And then also length constraint, and we'll play around with that a little bit. So let's go to player, to twit it, and create a new simulation that's basically this simulation, except we're going to add surface flex and length constraint to the simulation. And I'll give everybody a minute or two, a few minutes to do that themselves. And then we'll come back. Okay, so that's the exercise. Is it clear what the exercise is? In principle, you could add that by editing the simulation that we already have, but it'll actually be faster to create a new simulation from scratch and do it. So this is a little bit of a sanity check to see whether you remember how to use Wizard in Congress. So I'll give people a minute or two. I'll start a poll, and when you're done with creating the simulation, just answer the poll and let me know so I can keep track. And if anybody needs help, or forgotten something, something's not working, you can come back and let me know. We'll help you out.
I had a quick question.
Sure, please go ahead.
I was just curious, say that if you wanted to like explore, you know, like hundreds of different parameters, is it possible in CompuCell to like programmatically like set like every 500 Monte Carlo steps, change this parameter and so forth, and do that kind of stuff?
Absolutely. So
Okay.
I think as soon as we're done with this exercise, I'll talk about Python Steppables and doing things of that kind.
Okay.
I mean, conceptually, there are two ways to do it. You could run a whole bunch of simulations, each simulation of which had a different set of parameters.
Mm-hmm.
And if I'm going to throw things out on a cluster, that's probably how I do it. Run them independently. Then you have a lot of data wrangling because you've got a lot of files. The other one that I do a lot in teaching is exactly what you said, where at time step 100, I change the value of parameter x from current value to value plus 1. At time step 200, I add 1 to it again.
Mm-hmm.
And so those kind of things that I do, and I have a bunch of examples of how to do that. CompuCell, it used to be a little bit awkward to change some of the parameters in the XML. You had to use a slightly special syntax for doing it. Recently, it's gotten easier. And so Giuliano and TJ could update us on if there's a particular thing that you want to do that seems awkward, we could come back to that. But we'll do that all the time. We'll generally change parameters in Python rather than doing it by hand in the steering panel. As I say, as soon as we're done with this exercise, we'll come to that. Okay. So let me do it myself. This would be exercise 3.4.
So I have a quick question. I finished making it, and then I brought it up in CompuCell, and when I pressed start to play the simulation, I got a server disconnection. Does anybody know how to get around that? Because I've tried it twice to bring it back up, but it won't let me get back in.
So you killed the process and relaunched?
Yeah. I went, exited out, came back in, still did it. But I can open up other simulations.
Huh.
Which simulation is throwing the server error?
The one we just created.
I have the same problem.
All right. Well, let's see what happens when I do it. I wonder.
Are you all on NanoHub or the desktop version? Or
I'm on NanoHub.
okay, mine runs fine on the desktop, so it's probably an issue on that end.
Well, let me see what happens when I try to launch it.
Is it that directory pathing issue where you can't execute code in the root directory? You have to point it to your home.
Yeah, that's possible. Where did you save it?
I saved it with the rest of the other simulations that we've been making.
Okay, so then it's not that. Let me check my path name, because it's possible that I just was sloppy and did the same thing. So let me try. Let me see where
It's on your home.
This
it's
is
at
okay.
the top of to edit.
This is okay. So this is all right. It's in my directory, so I have write privileges there. So let me try opening it in Player, see what happens. Yes. So it seems to work for me. So is it freezing? Is it? You say it's throwing. Showing a disconnect error.
Yeah, like it'd say a server disconnect error. I'm trying to remake the simulation, making sure I follow my pathway with the folders. I'll see if it behaves this time.
Because those server disconnects are usually syntax errors in XML.
Yeah,
Could
and
be a Python failure.
yeah,
But there's nothing in this that should be failing. In other words, the default should work.
yeah, I've seen that error when I misconfigured a new tool or something.
And so, did anybody else get it to work on NanoHub? Because I'm running it here on NanoHub and it's working. And so did somebody else said it crashed for them? Who else said it crashed?
Me, it crashes for me on NanoHub and on the desktop. I tried to run it multiple times already. I think I should probably have to restart my machine or something like that because I've been doing some other stuff today. So
No,
there's a possibility.
No, it shouldn't be. Nothing that we've done should be causing that. And in principle, the player could have an internal state that was messy. But does anything else run, or or everything except this runs?
I think everything except for the simulation has been running. I can play with it later, but I can just follow along.
Oh, I'm sorry, because I wonder what could be. I guess the one thing I did was I did not make the cell lattice 100 by 100. I left it as 256 by 256. So I did not follow the instructions in that. I wonder if that was the issue. That would be the issue.
I left mine the same as the default setting as well.
And you clicked just these 4 boxes, and you added cell type.
Yep.
Okay. Well, I'm sorry. I don't know. I could.
It's okay.
You're not alone, Jessica. I'm here too with the same problem.
Okay. So I want to talk a little bit about something that we've used already, which is blob initializer and uniform initializer. And if we look at the code for those, the code for those is here. And these blob initializer draws a rough circle, and uniform initializer draws a square, rectangle. If we drew uniform initializer, we have box min and box max that define the corners of our domain. If we use blob initializer, we define the radius of the circle and the center. And then we have the width. It draws square cells, width by width. Gap allows us to put a space between the cells if we want to. And then in this case, the simulation, we only have one cell type to begin with, so there's nothing to do. If we had multiple cell types, we could list the types of cells, and they'll be randomly distributed in this domain. And there's a little bit of a trick. If we list cell type 1 5 times and cell type 2 once, we'll get 5 of cell 1 for 1 of cell 2. The one thing that's a little odd in the XML is you can't have a space in the list. When you type cell 1 comma cell 2, you can't have spaces. I'm explaining this here because if we wanted to only have one cell to begin with, we could use the blob initializer and say that the radius was smaller than the one cell. We'll only create one cell. Or similarly with box, if I adjusted the min and the max so that there was only one cell drawn, I could do that. Another thing that I can do is I can have as many regions as I want. So I could draw a circle here, circle here, circle here, circle here with different properties. Not the most elegant thing in the world, but it's helpful to have. Okay. And so now And if things haven't worked, then perhaps it wasn't the best choice in the world. The next exercise was to change the initial conditions to make a single larger cell. And so I've said to use, so how could I do that? Well, I can just change the size of the cell to be 20, for example, here. And if I save that and now run that, see if maybe it'll crash on me now. No. So stop. Notice the initial cells were bigger. Let me run that again. See, the initial cell size is larger. If I go back to my here, and I really wanted to only have one of them, make it 100. Well, I have 4 instead of 1. Notice that my targets are still what they were, so these cells are going to shrink extremely rapidly to the target cells. And I wanted to have a single cell. Here I happen to have 4. And I'm not going to get through everything that I wanted to do for this class, which is okay. I'd much rather cover the material and have everybody understand what we've got and feel that it's comfortable to people. This isn't a prerequisite for anything, so we get through what we get through. So if it's painfully slow for people, send me an email saying that. If it's too fast, send me an email. If it's too fast, speak up in class. If it's painfully slow, you can express that, but as well, you're welcome, and I will try to adjust. But I want to now, if possible, have everybody create a simulation which creates just one cell. And for my case, I'm going to have to change my editor a little bit. I can make box min and max a little bit closer together, so I only get 1. You're free to play with that. Try to figure out how to create a single cell. So everybody, your assignment is to create one cell, run it, and watch what it does. Oops. I don't know why you want to see that. There are a number of ways one could create a single cell.
Perhaps I missed the explanation, but why does the cell shrink after the initial steps?
Because, good question. I did not change the target volume of the cell. So I made the initial volume 100 by 100, so 10,000, but it still has a target volume of 50. And if you're done with that and people are waiting for people, you could go in and try changing the target volume by hand and seeing what happens. We can change lambda volume by hand and see what happens.
When you set 100 on the width, is actually 100 by 100, right? Voxels.
Yeah, and in that
Okay.
drawing, it's linear dimension. Width is on linear dimension. 100 by 100 would be 10,000 voxels. And there's something that we'll find, which is we talked about making the surface energy too large, that freezes the cells. Another thing that will freeze cells is if you make lambda volume very big. And so if you want to build, there's an option in CompuCell called frozen, with which the cell boundaries don't move. But sometimes you want them to be able to move a little bit, but not very much. And one way to do that is effectively what plant cells do, which would be to make the lambda volume very large. And very large may actually be pretty large, yeah? And the cell will freeze. And so that's one of the things that we can explore, is the effect of changing the constraint strength. It's an interesting question. Why does it freeze when you make the lambda volume very large? That's something to think about. So does everybody have a single cell? At least everybody wants to have a single cell. Okay. So the last thing I want to do today, and I think this is important, and it is needed for the homework, so I want to go over it, is to come back to the question that was asked earlier, which is how do we change things in the simulation while it's running without hand editing it? And to do this, we are going to use Python. And I promise you that the amount of Python we will need for this class is not large. There are the one concept that we will have to get used to, which is Pythonic and may be unfamiliar to people, is the concept of a dictionary. And maybe a little bit of lists. And so those are two basic Pythonic concepts that we will deal with. But in general, the Pythonicity of what we do is not that big. There are a few places where we'll run into Python annoyances, but we'll try to avoid those. And so I'm going to be talking about using Python in model specification. And we'll use Python to do things like cell division. We'll use Python to do things when we want to do analysis, when we want to plot things, when we want to save files. And we're going to use Python when we want to go in and change things in particular ways. The cell's going to differentiate. The cell's going to change its adhesion. The cell's going to grow. All of those kind of dynamic things are going to be specified in Python. So we'll come back to this image that we had before, which is alternating steps where the cells move with steps which are called pot steps, with steps where other things happen, which are called steppables. And those steppables might include updating the intracellular network states. They might include having diffusion happen, might include having cells secrete or absorb chemicals, might include cells dividing or dying, might include doing statistics. And so typically what happens is there's one sweep of the cell lattice, which is called the Monte Carlo step, through the cell movement. And then the cell lattice is frozen for just a minute. And then you run all of the other things called steppables that go in between the steps of updating the lattice. Now, in general, that time unit of one Monte Carlo step can be interpreted pretty elastically in terms of real time. But if I know what the scale of the cell is in voxels per micron, or microns per voxel, and I see that the cell moves at a given speed, and I know experimentally how fast it moves, then that gives me a calibration on the time step. In general, these steppables are run once per Monte Carlo step. So I run one sweep of the lattice, then I run the steppable, one sweep of the lattice, then I run the steppable. If I want to call the steppables less frequently, like I want to save data to a file, and I only want to do that every 100 Monte Carlo steps, that's not a problem. If I want to call the steppables more often than once per Monte Carlo step, I have to do a little bit of fiddling. And the reason for that is that fundamentally, as I mentioned, time is not well defined over short time intervals. And so doing things multiple times within a Monte Carlo step is a little bit violating some of the principles of the simulation. But there's no algorithmic reason you can't do it. You just have to be careful. And it's a little less convenient because we don't encourage. Okay. And so remember, when we look at our, let's look back at our code. Our code consists of 3 blocks, something called exercise 3.4 here, .py, which is called the main Python script. And most of the time, we won't even pay attention to that. Occasionally, we'll have to edit it when we're doing things by hand. In general, Wizard Hand creates that for us, so we don't have to worry about it. Exercises 3.4 ML, which is what we've been looking at, and then something called exercises 3.4 steppables.py. And so far, we haven't done anything with that. And if we look inside of the steppable, what we will see at the top, and actually the syntax has changed a little bit. It's been simplified from what we have here. This is an older version of Python, a CompuCell. From CC3D core, PySteppables import star. That's importing all of CompuCell. So it's available in Python. And steppables are something called a class. And if you're not familiar with classes, you can think about these as functions or methods. In CompuCell, in Python, they have particular meaning. And in general, there's going to be, and in some of the older versions of CompuCell, there would have been a lot of header information here, which has been hidden from us. But the class inside of it will be, and we can have as many of these Python steppables as we want. Each one will be called once per Monte Carlo step or once per n Monte Carlo steps. And inside this class, we will see something called an init. And that init will have a self in it. And again, if you're not a Python person, you'll discover selves show up occasionally. And occasionally there'll be a question of, do you need a self or not? And usually the answer is yes, but if it doesn't work, try it the other way. And then there is something called frequency. Unfortunately, frequency actually is interval, it's period. It shouldn't be frequency. And this is how often you're going to call this step in terms of Monte Carlo steps. Frequency equals 1 means you call it every Monte Carlo steps. Frequency equals 10 should mean you call it 10 times per Monte Carlo step. In fact, it means you call it once every 10 Monte Carlo steps. So it should be interval or period. And then inside of this, you will see, here we're talking about the frequency, you will see the init. In the init, you issue Python commands that are started before the beginning of the simulation, before time 0. The start is called at time 0 and just once. And we're typically going to use that to do things like configure the cells, set their parameters, and so on. Step is called once every frequency Monte Carlo steps. And typically in the simulations we're going to do here, we're going to interrupt the simulation, not let it run to completion. But if I said that the simulation runs for 1,000 Monte Carlo steps and actually gets to 1,000, before it stops, it would run the finish function. And the finish function could be used to output data when you're done with the simulation. And boy, when did this show up? I don't even know that. What is that? Shows you how.
Yeah, that one is kind of weird. It gets called if you hit the stop button in player.
Okay.
So what I usually do is whatever I want to do in the end of the simulation, I define it either in finish or in on stop, and then I call the other from the one, and they do the same thing.
That's very convenient, but I didn't. That's news to me. I hadn't run into that. Okay. So okay, so dealing with the fact that normally we interrupt the simulations, there's now a function that handles that interrupt case to output whatever the configuration. If you want to save your configuration. Okay, that's new. That thank you. It's a good thing you're here.
Yep. Okay. I still think that hitting stop should just call finish, but anyway.
Okay. One thing that we have to remember in Python is that indentation is important. Python likes indents rather than parameters. If you're not a Python person, indentation matters. Fortunately, Twidit helps you with indentation. It's if you do not have your lines aligned within a block of code, it will crash. And when you start out with Python, that's one of the biggest annoyances of Python. And after a while, you're so used to it, you wonder why all languages aren't written that way. All right. Okay. We can have multiple steppables in CompuCell, and Twidit allows you to add steppables. If you go under CC3D Python, at the bottom there's add steppable. Don't do that right at the moment, but add steppables. That would create another line here, which would create another block of code. Why would you want to have more than one steppable? Well, a lot of the time when we're working in class, we'll put everything into one huge steppable. But if you're going to build modules that you're going to reuse, you might have a module that displays the graphics. You might have a module that implements the subcellular elements. You might have a module that implements the statistical analysis. And you might want those to be reusable. In that case, packaging them in separate steppables means that you can pull them out and use them as code blocks. So that's a reason that you might want to do that. We'll also find that if we're going to do cell division, we need a special steppable that has certain special functionality. And so there'll be something called mitosis steppable. And so one of the times we're likely to run into multiple steppables is when we have mitosis implemented, cell division. Okay. So cells. So now we're going to talk about, and again, some of the language that I'm going to use here is things that some years I've defined earlier in the class. And this year I've pushed them off a little bit because they tend to be sort of abstract until you've done it. And so you'll see the word objects floated around a lot. Now in object-oriented language, we're used to computational objects. In a modeling context, objects mean something slightly different. Cells in CC3D are Python objects, and they have a handle. Objects are referenced by something, a pointer effectively. And typically we will give that handle the name cell, but it could be aardvark. It doesn't matter. It's just a variable name. And remember that each cell has a unique identity. And one of the things that we're going to do a lot is we're going to want to know about cell attributes. And cells have a variety of attributes which are accessible directly. These are some of these things you need to implement by hand. But in general, most of these attributes are automatic. I said you don't get anything for free. You get some things for free. Cell.id, cell number 1 or cell number 277. Cell.type, is this my cell, medium, or something else? Cell.volume, how big is the cell? That's always going to be there. Cell.target volume will only be there if I have a volume constraint. Cell.lambda volume, how strong is the volume constraint? Cell.pressure, that's new, is that pressure term, that pressure force that I defined before. Cell.surface tension is before. And there's a list. If I want to see what I can do, I go under CC3D Python, cell attributes, and if I don't remember the syntax, I can ask it to paste in, I want the center of mass of my cell, cell.x center of mass, y center of mass, c center of mass. So Twidit has code snippets, templates for most of the things that we were going to do pretty often. They're not always configured with the most useful defaults, but they're there. Okay. Another thing that we're going to do a lot in CompuCell is iterate over things. So these are loops. Now, biologically, we don't really have loops very much. And computationally, inside of CompuCell, these iterators should be thought of as doing something to everything at the same time. Really, we should be thinking about these things happening concurrently rather than sequentially. Python encourages you to think about iterators that way. But the one that we're going to use all the time will be this one here, for cell in self.celllist. Self.celllist is, as it advertises, a list of all the cells in the simulation. If I do for cell in self.celllist, that will run through every cell in the simulation. In this case, it's going to print the ID of the cell, not do anything very exciting with it. But I could do something more elaborate. I could make the cell grow. I could make the cell disappear. There are a bunch of different iterators that are available. And again, if I go to CC3D Python and I go under Visit at the bottom, that gives me the options that are possible. I can go to all cells. I can go to all cells of a given type. Clusters are for when I build subcells, when I build cells with internal structure, which we haven't gotten to yet. I can iterate over all pixels in the lattice. Strongly recommend against doing that. It's slow and annoying. Cell boundary pixels is interesting. If I want to know what's just inside or outside of a cell, I can iterate over those. And that can be pretty useful. I can iterate over the neighbors of a cell. I want to know who I'm next to. Am I next to cells 1, 15, 37, and 29 or not? All the cells in a pixel, all the pixels within a cell, and again, all of the components of a cell. For the moment, we're going to focus on all cells and occasionally cell neighbors. And if I go into my Python, I can paste in an iterator, iterate over cell neighbors. For neighbors, this one has a slightly Pythonic syntax. It's got two things on the left-hand side of the equal sign, which is a little bit unusual. In self, get neighbor list. We'll go over that one later. For the moment, I just want you to focus on for cell and self.celllist, which we'll use a lot. Here, I print cell ID. It'll just print me a list of all the cells I've got. And now I'd like to talk about plotting things. And we're going to run out of time in about 5 minutes, but I want to at least get this done so we can do the homework. So, as I mentioned, Twidit provides a lot of functionality to do things that we're going to do pretty commonly. One of the things that Twidit will help us do is create plots. And so, if I go to CC3D Python and I go to scientific plots, it will give me a setup, an add data points, a refresh plot, which we don't need, erase plot, and a few other things. And it'll tell us, in the case of setup, that this belongs in the start function. And it'll tell us that adding data points belongs in the step function. And so what I'd like people to do here is go into the start function somewhere. You can create a blank line for yourself to do it. And go to scientific plots and do start. And unfortunately, this is going to show up a little bit truncated because of the scale, because of the screen size. But I can see it all here. It's going to put in the following lines of code. It's going to create a line that's called self.plot_window. And this is plot_window is a handle. It's a reference. And to create a plot, first thing I have to do is create a window for that plot, because the plot has to be put on the screen. So it's creating an empty window to put the plot in. And then I'm going to say what's inside of that plot, and it's going to create a set of axes. Self.addNewPlotWindow, and I give the plot a title, the x-axis label, the y-axis label, and then I have some options. Is it linear? Is it logarithmic in the x direction, the y direction? Do I have tick lines, grid lines, and so on? And that's going to create a plot window that I can then plot into. And then there are going to be two lines here, self.plotWindow, add plot, and this is going to create a data series. In this case, it creates a data series called mVolume and mSurface. And I can say, is it lines, is it dots, is it other things? What color are they, how big are they, and so on. And so I will have to remember what the handles are, because when I want to add data to this plot, I'm going to have to reference them. Does that make sense? Once I have created a plot, I can add data. So, for example, suppose that I actually wanted inside of my step function to plot the volume and surface area of every cell in my simulation. To do that, I go into this for-cell and self.cellList loop. I go back to my CC3D Python. I go to scientific plots and I do add data points. And here it puts in self.plotWindow. That's a reference to plot window here. If I had two plot windows, I could call them plot window 1 and plot window 2. I could have as many as I wanted. And then I'm going to add a data point. And I have to tell it where to add it. mVolume has to match up with mVolume up here. And here I'm going to plot on the x-axis the time and the y-axis the cell volume and surface area. The name of the handle, plotwin, has to match exactly what I had here. If this was plotwin3, it would have to be plotwin3 here. The name of the data series, mvol, has to match exactly down here. Okay. If I run this, it should run. So let's see what happens. Trace back. All right. Invalid syntax. Which crashed. Self plot window, so add new plot window. Huh. Let's see what I did wrong. Did I put it in the wrong place? That's the most likely thing. Ah, these aren't indented. Still a problem?
Could you go back to the code? I think I saw. Def start, is there not, there's no
Oh,
there's no colon or.
What happened to my, okay, I don't know how I clobbered my, sorry, thank you. My problem. I don't know how I managed to erase that. Thank you.
No, I think it might, I remember I generated a simulation for the second homework and then one of the XML tags was empty. So I think CompuCell might mess up sometimes, I'm not sure.
All right, so let's see. Boy, I'm not doing too well tonight on the fly here. Line 140. Steppables start missing one positional argument, MCS. Oh, because there's no MCS in the start function. That's my mistake. Okay. Typing things by hand is the problem. Did it work for other people or did it fail? There we go. So is everybody able to get that? That's where we'll stop. If I can get people through this, we're in good shape. It's not very exciting here at the
I had a couple of questions.
Okay.
First, what version of Python does CompuCell use? Do you know?
3.7, isn't it? No, 3.
The one in NanoHub, I think, is 3.6. The
3.6.
most recent CompuCell is 3.7.
Okay. And also, Andrew asked in the chat, does the plotting in CompuCell use matplotlib or is it its own library?
PyQt-Graph.
PyQt-Graph, okay.
Yeah. It's a weird one. There are or were conflicts between matplotlib and CompuCell. That's why.
Okay.
Yeah, the plotting functions are variable in their operation. The whole plot libraries were changed some years ago, and the plots in principle have a bunch of features which may or may not work the way they are supposed to work. When you hover over a plot and right click it, it'll give you a bunch of options. Some of those may work, some may not work, some may crash. One thing that is nice is that it has an export, so you can save the plot as you're running by hovering over it. Some of them I know don't work. The transforms are grayed out because they don't work. Okay. But does everybody, I want to make sure everybody can get the plot to work. So that's really where I was trying to go tonight. You'll see this. Initially, the cell was very big. It shrank. Surface area went up and then went down. The fact that I've got a fixed scale means that what I'm seeing on this plot is not very exciting. So I should probably rescale the vertical axis. I could put it on I think I can change the y-axis to log scale. Actually, it doesn't give me the log scale option anymore, does it? It used to. Let's see. Does that work? Doesn't look like it's letting me adjust it, so I'm not gonna update this one. But did everybody get the basic plot to work? Anybody have it not work? Within the plot itself, I have to look up typically what my options are. There are quite a few. I could make the scales log instead of linear. Let's do that. Make the y-axis logarithmic. Looks like it actually didn't. The log scale didn't work. Yeah, which is interesting. Maybe it's on. Maybe one is all right. The infinity, I don't know where that's coming from. So there may be some issues with the labeling of plots, at least on NanoHub. But the actual values of the plot should be all right. So again, what we've done here, just to review before we break, is we created a plot window. I use the defaults. I have the volume of the cell as one series, and I'm plotting cell.volume for each cell. There's only one cell, so it's not a problem. I'm plotting surface area for each cell. If I had 20 cells, I'd have 20 points at each time point. Another thing that I could do, and this one maybe is a little bit more interesting, is if I wanted to plot surface area versus volume, what would I have to do to change it? And that'll be the last thing tonight. Instead of plotting, don't worry about changing your axis labels. What would I have to do though to plot on the x-axis, plot the cell volume, and the y-axis, plot the surface area? I'll give you a hint. I have to change 2 lines of code. 3 lines. Well, how many plots do I need if I'm going to plot just surface area versus volume? Do I need one series or 2 series? One. So remember, the comment in Python is hash. So I'll comment out that second data series. And I'll comment out that second data series here too. I've gotten rid of. And now here, in my first data series, I was plotting MCS on the cell volume. Thank you. And I appreciate that. We're almost done. I'll finish in about 10 seconds. So thank you for being patient. I'll take cell surface. I'll make the x-axis surface and the y-axis volume. I could go the other way. And I'll just replace time, MCS, by cell surface. And let's stop, save that, and let's run it and see what it does. And so now I can see the trajectory. I'm not exactly sure why it's gotten so slow here. There we go. And I can see the trajectory. The cell surface area went up. The volume has been decreasing. And so this is now the trajectory of that cell in volume versus surface area space. Okay. So that's as far as we're going to get tonight. I appreciate people letting me run over a little bit. Sorry about the snafus with getting into NanoHub. Now I've got my account fixed, so that should be all right. Any questions before we break? I think that the homework assignment should be okay. I don't think there's anything in it that references things we didn't cover today. If there is anything, email me about it or come back to me. The rest of the exercises we were going to do were basically taking this cell and manipulating it in various ways. But I think you could do those on your own. The slide deck is there. We may come back and do one or two of them together next week, but I think these are things that we can explore on our own. Okay, thank you everybody. Appreciate your patience. And I look forward to talking to you. Please, people who are going to do projects, please try to get an appointment with me. As in principle, between now and the end of the week, which may be hard because my time is busy, but at least if we do half-hour slots, we can at least talk a little bit. I'll do my best to get everybody scheduled so we can have a good conversation. Okay, good night.
Night.
All right, thank you.